Welcome everyone to the pre-recorded lecture for solid geophysics for today, 30th October. We have been discussing about stresses and we ended our class in defining differential stress. And we said differential stress is the difference between maximum and minimum stress. And we said why differential stress is very important because it controls essentially deformation, right? So we will continue with stress and we'll get into more details of stress in structural geology next semester. But today, what I want to discuss is about strain, and then we will try to correlate. We will see some, you know, elementary relationship between stress and strain, which will be useful for your lectures on elastic wave propagation. So let's start with strain. So what do I mean by strain? Strain is essentially a measure of deformation, right? It's a measure of deformation. And this is, of course, if stress is cause, apologies, if stress is cause, and then strain is this strain is its effect, okay? So for example, I have a piece of material, okay, which I am suppose putting under tensile stress, okay. So I'm trying to extend it. What would happen after that? That this material will essentially get extended but thinned. Okay. So this is before deformation. This is stage one, and this is after deformation. So we will say that this particular piece of material has been strained now because of the application of that force F, right? Which is extensional force. And then the way we would define its deformation, we will call it as strain. So strain in generally is subdivided into three basic categories. One we call as longitudinal strain. The second we call as bulk strain, or this is also called volumetric strain. And the third is shear strain. Now let us look one by one. What are they? So let's begin with longitudinal strain. Okay. Suppose I have a line element which has a initial length of L0. Okay. And then, of course, after doing some, after putting it under some stress, the length becomes L1. Of course, L1 can be lower than L0 or higher than L0. For the sake of simplicity, let us say L1 is greater than L0. So I am eventually extended that line by applying some stress. So strain, or in this case, particularly longitudinal strain, which we will denote as epsilon, is equal to L1 minus L0 by L. Or L1 minus L0 we can write as delta L by L, right? So delta L is nothing but L is nothing but the uh, difference between the initial length and the final length after deformation. Similarly, we can define volumetric strain, or we also call it as bulk strain. Suppose I had a sphere, okay, which had a volume of initial volume of V0, and up after applying some pressure, V0 becomes V1. So volumetric strain or bulk strain is V0 minus V1 by V0. Okay, here I have considered V0 is greater than V1. Of course, it can be the other way around too. So this is bulk strain. Then the third category is called, of course, shear strain. Let us consider square or a rectangle, and then let us say we subject it to some shear stress. You know, this is how shear stress is actually denoted. So what happens that, you know, perhaps the bottom side of it is fixed to the surface. So after deformation, the shape of the square looks something like this. Okay, and then say for example this angle is theta. So shear strain will be measured as tan theta. Okay, as simple as that. So we have defined longitudinal strain, volumetric strain, and shear strain. And this is the measure of the deformation. Okay. Now let us see how these three individual type of strains are related to stresses. Okay. So now let us look at, so longitudinal strain has to be related with your normal stress, right? Why? Because simply if I have a line and if I want to extend it, I have, or if I want to shorten it, either way, you know, I have to either put compressive stress or extensional stress, but that has to be normal stress. So how they are related? So now if I essentially try to draw a stress strain curve, let us say I plot here sigma. Okay. So that is my sigma n. But then this sigma n is not the absolute value of strain. It has to be the differential strain. Okay, so this sigma n is nothing but sigma 1 1 minus sigma 3 3, where sigma 1 denotes maximum stress and sigma 3 3 denotes minimum stress. Okay, and in the y axis I have plot epsilon. Okay, so what I will observe that up to a certain limit, if I keep on increasing my differential stress, I will see an increase in my longitudinal strain as well. So if my differential normal stress is increasing, my longitudinal strain would also increase. Okay, but as soon as I remove my stress, what I would see that uh, my body will not retain the deformation; it will come back to its original place. Okay, and that will happen up to a limit. Okay, and that limit we call as elastic limit. And this phase of the deformation, where stress essentially varies linearly with strain, stress varies linearly with strain. And remember here, stress means the differential stress. Stress varies linearly with strain. And so the conditions are, so till elastic limit, sigma n will be directly proportional to epsilon. Okay. And the second condition is if we remove sigma n, yeah, epsilon will be 0. Okay, so it's completely recoverable deformation. Okay, this is recoverable deformation. Yeah, and what happens after elastic limit? Depending on the material, either it breaks. Depending on the material, either it breaks or either so after elastic limit, either the material breaks or plastic deformation starts. Okay, either the material breaks or plastic deformation starts. But we will discuss in detail about plastic deformation later on. Just give me one moment. Just one moment, please. Okay, so Sorry for that. So after the elastic limit, either the material breaks, so then that is called an yield point, or plastic deformation starts. So the stress strain behavior, can progress like this, or it can progress like this, or progress like this. Now we will discuss about plastic deformation later on, but it's not exactly relevant for us at this moment. We will keep our discussion limited up to the elastic limit because we are discussing about the elastic wave propagation. So it's important to understand what is elastic limit. So elastic limit is uh, till the limit of that material, where sigma n and epsilon varies in a really linear relationship, and if we remove sigma n, epsilon becomes zero. That means it's a completely recoverable deformation. Okay, and this is what we call as the elastic limit. Now, this particular formula, if we write here, sigma n is directly proportional to epsilon, and I can equate that, or sigma n is equals to, you know y epsilon. So y here is called the Young's modulus, right? Young's modulus, okay? And this particular equation is called Hooke's law, right? This is Hooke's law. I'm sure you have heard about Hooke's law before. So this is how longitudinal strain and normal stress is actually dependent with each other, and that is how we have defined the elastic limit. Now, if we see how do we define elastic limit for bulk strain and for shear strain? So, in case of bulk strain, we have to consider bulk strain is volume change, right? Volume change, either volume enhancement or volume reduction. So, bulk strain we have to relate with pressure, okay, which is isotropic. Okay. So, in this particular case, what I will draw in my x-axis, in my y-axis pressure, in the x-axis I will draw your bulk strain. Yeah, and then of course there will be a limit after which the elastic deformation limit will stop, and the corresponding modulus is called bulk modulus. Okay, corresponding, like Young's modulus, the corresponding modulus is called modulus. And similarly, for shear strain, what would I relate it with for shear strain? Shear strain is related to shear stress, of course. Okay, and we will draw uh, shear strain in, maybe we denote shear strain with this symbol, and then shear stress will be, of course, tau. Then there will be the elastic limit, and the corresponding modulus is called shear modulus. Okay, so now how now I would like to define a term which we call as rheology. Okay, so rheology means the mm, behavior of a material, for us it is rocks, when it is subjected to stress. Okay, so that particular uh, so rheology can be broadly subdivided into key categories, and we can put them as kind of a in a ternary diagram. The first one is elastic, which we have just discussed. The second one is called plastic, and the third one is called viscous. Okay, and there could be in between members as well, like elastoplastic. There could be viscoplastic. There could be elastoplastic. There could be viscoelastic, and there could be viscoplastic as well. Material. Okay? Elastoplastic, viscoelastic, and viscoplastic. But for what is a plastic material, what is a viscous material, we will discuss them in detail later on in next semester. But for the time being, remember, we are only interested in the elastic rheology. Okay, because and how elastic rheology is defined. Elastic rheology is defined when something gets strained linearly with stress, and as soon as you remove the stress, strain is recovered completely. Okay, that is how we define elastic materials, and then it can be expressed in terms of bulk modulus, shear modulus, and Young's modulus. Okay, depending on what type of stress strain combination we are looking at. Okay. So, but of course, we will see these elastoplastic, viscoplastic, and viscoelastic material in the next semester. There will be some other complex combinations like Kelvin material, Maxwell material, then Brigham plastic. Okay? But those are subject to the discussion in the next semester. Okay? Now, there is one more thing that you need to remember, that the rheology of material is dependent on primarily three things. Okay, one is temperature, the other one is pressure, and the third one is called strain rate. Okay, so the same material would behave in a different way in room temperature and at an elevated temperature, maybe in the mantle condition. Okay. Also, there is a huge effect of pressure on materials rheology. Pressure means confining pressure. Okay, confining pressure. Whether confining pressure is high or low, that determines the fate of the material while we subject it to external stresses. And of course, strain rate. And strain rate means whether your deformation process is faster or whether your deformation process is slower. Okay, that would essentially guide what sort of rheology would be there for that particular material when we are subjecting it to stress. Okay, so now we have got some idea about stress, some idea about strain, and we have understood what elastic materials are. What elastic materials are. Okay, so based on that knowledge, we are going to understand the theory of elastic wave propagation. Okay, elastic wave propagation. So this is how we are going to tackle this particular chapter in the next class, from next class onwards. So what we have already done is to have the some pretext around pretext or preamble around stress, strain, and elastic material. Okay, and then that will lead us to you know some basics of wave propagation. In the basics of wave propagation, which we will start from next class, we will basically see wave equations, and then we will see you know uh, how the wave equations vary for P and S wave. We will see there is something called surface wave. P wave and S wave together is called body wave. Okay, we will see why, how body waves are different from surface waves. Okay, so we will uh, form up some basics about the wave propagation, and that will lead us to essentially earthquake seismology. Okay, where we will see how P wave, S waves, and everything propagates under when there is an earthquake, how to detect an earthquake, how magnitude of the earthquake is defined, and everything. And then finally, we will talk about exploration seismology. So that would kind of end our chapter on the elastic wave propagation and seismic. So I will just stop the lecture here today, and we will continue with the basics of wave propagation in the next class. Thank you.